into products is called as reaction mechanism. Principles explain reactions are fission of a covalent bond. A covalent bond can get cleaved either by 1. Heterolytic cleavage or 2. Homolytic cleavage. In heterolytic cleavage, the bond breaks in such a fashion that the shared pair of electrons remain with one of the fragments. Example, heterolytic cleavage of bromomethane CH3 plus and Br minus as shown here. A species having a carbon atom possessing sextext of electrons and a positive charge is called a carbocation. Example, ethyl cation, a primary carbocation, isopropyl cation, a secondary carbocation, tertiary butyl cation, a tertiary carbocation. Order of carbocation stability is. These have triagonal planar shape with positive charge. The heterolytic cleavage can also give a species in which carbon gets the shared pair of electrons and is called carbanion. Example, when group Z attached to the carbon leaves without electron pair, the methyl anion is formed. Homolytic cleavage. In this type of cleavage, one of the electrons of the shared pair in a covalent bond goes with each of the bonded atoms. The single electron movement is shown by half-headed fishhook curved arrow. Such cleavage results in the formation of neutral species, atom or group, which contains an unpaired electron. These species are called free radicals. Homolytic cleavage can be shown as alkyl radicals are classified as primary, secondary, or tertiary. Alkyl radical stability increases primary to tertiary. Organic reactions which proceed by homolytic fission are called free radical or homopolar or nonpolar reactions. Nucleophiles. A region that brings an electron pair is called a nucleophile, Nu. That is, nucleus seeking, and the reaction is then called nucleophilic. In a polar organic reaction, a nucleophile attacks an electrophilic center of the substrate, which is the specific atom or part of the electrophile, that is, electron deficient. A curved arrow notation is used to show the movement of an electron pair from the nucleophile to the electrophile. Example, hydroxide, HO minus, cyanide, NC minus ions, and carbanions, R3C minus. Neutral molecules such as H2O, R3N, R2NH, etc. Electrophiles. A region that takes away an electron pair is called electrophile, E+, that is, electron seeking, and the reaction is called electrophilic. The electrophiles attack at nucleophilic center, which is the electron-rich center of the substrate. Example, carbonyl group or alkyl halides R3C single bond X, where X is a halogen atom. Inductive effect. Polarization of sigma bond caused by the polarization of adjacent sigma bond is called inductive effect. Example, chloromethane CH3 CH2Cl, in which the C single bond Cl bond is a polar covalent bond. It is polarized in such a way that the carbon 1 gains some positive charge and the chlorine some negative charge. This effect is passed on to the subsequent bonds also, but the effect decreases rapidly as the number of intervening bonds increases and becomes negligibly small after 3 bonds. Halogens and many other groups such as nitro, NO2, cyano, CN, carboxy, COOH, ester, COOR, aryloxy, OAR, etc., are electron withdrawing groups. Resonance structure. The resonance structures, canonical structures or contributing structures, are hypothetical and individually do not represent any real molecule. Many organic molecules whose behavior cannot be explained by a single Lewis structure. Example 1. Benzene. This can be represented equally well by the energetically identical structures 1 and 2. It is a hybrid of the two structures 1 and 2 called resonance structures. Example 2. Nitromethane CH3NO2. 2 N single bond O bonds of nitromethane are of the same length, intermediate between a NO single bond and a NO double bond. The actual structure of nitromethane is therefore a resonance hybrid of the two canonical forms 1 and 2. The difference in energy between the actual structure and the lowest energy resonance structure is called the resonance stabilization energy or simply the resonance energy. Rules applied while writing resonance structures are: the resonance structures have 1. The same positions of nuclei and 2. The same number of unpaired electrons. Resonance effect. The resonance effect is defined as the polarity produced in the molecule by the interaction of two pi bonds or between a pi bond and lone pair of electrons present on an adjacent atom. There are two types of resonance or mesomeric effects denoted as R or M effect. 1. Positive resonance effect. Positive R effect. In this effect, the transfer of electrons is away from an atom or substituent group attached to the conjugated system. Example: effect of aniline. 2. Negative resonance effect. Negative R effect. This effect is observed when the transfer of electrons is towards the atom or substituent group attached to the conjugated system. Example: in nitrobenzene, the electron displacement can be represented as atoms are substituent groups representing positive R or negative R. Electron displacement effect R. Positive R effect. Halogen OH, OR, OCOR, NH2, NHR, NR2, NHCOR. Negative R effect. COOH, CHO, C double bond O, CN, NO2. Electromeric effect, E effect. It is defined as the complete transfer of a shared pair of pi electrons to one of the atoms joined by a multiple bond on the demand of an attacking regent. It is a temporary effect and is represented by E. 1. Positive electromeric effect. Positive E effect. In this effect, the pi electrons of the multiple bond are transferred to that atom to which the regent gets attached. Example 2. Negative electromeric effect. Negative E effect. In this effect, the pi electrons of the multiple bond are transferred to that atom to which the attacking regent does not get attached. Example: hyperconjugation. It involves delocalization of sigma electrons of C single bond H of an alkyl group directly attached to an atom of unsaturated system or to an atom with an unshared p orbital. It is a permanent effect. Example: CH3 CH2 plus ethyl cation. Hyperconjugation is also possible in alkenes and alkylanes. In case of alkene, hyperconjugation can be depicted as here. The hyperconjugation may also be regarded as no-bond resonance.